All right, so this is what we did the last class, where we came up with a concept of how we could find our break-in or breakaway points for the root locus. And remember, it only breaks away or breaks into the root locus when we have a complex conjugate pair. So essentially, the way you know that you have a breakaway point or a break-in point is if you have two poles or two zeros on the x-axis, and the you know that you're between an odd and an even, so you know that there's a root locus that lives there, but it either the root loci haven't been able to terminate or they haven't been able to start. So what I mean by that is if I have two poles and this is 1 to 2, I know that there's a root locus that exists between those 2 points. And I know that I start at those poles, but I have to end at a 0. So in this case, I haven't met my criteria of ending at a 0. So I must have a breakaway point. Similarly, for two zeros, if I've got this, and let's say this is 3 and 4, then I know by the rule that our root locus lives on the real axis between points 3 and 4. But we know that we started a pole and ended a 0, so our arrows are going towards the finite zeros, the finite open loop zeros. We haven't started on the real axis, but we have 2 points that end on the real axis. So at that point, we have to have a point, or we have to have something that goes in, right? So this is another reason why I've been spending a lot of time with our discussion about thinking about how to actually create these plots. It really makes sense to take it slow and to come up with a concept of how do we actually, interpret results, kind of figure things out, et cetera, et cetera. Okay. So those are our points. Now we're going to go ahead and move to our next concept, which is what if I'm a point here that I'm either a complex conjugate pair that's a real root that does not start these are actual, I shouldn't say real roots, these are valid roots that are they are open loop poles of our system, and we aren't on the real axis. So at this point, which way do we go? Do we go to this direction? Do we go here? We don't necessarily know the direction of where to start taking off. And that's the thing about drawing the root locus, is we have to have some sort of sense of where we're taking off and which direction we go. It's the same thing for a couple of finite zeros where we know we are going to end up at this location, but are we going this way? Is it this way? Et cetera, et cetera. We just don't necessarily know. So those are going to, it's going to help us to know what are the angles we depart or arrive at a complex pole or zero. Now, think about that for a little bit. What is there a tool, or is there some sort of a characteristic that we can use that will help us figure out what that angle needs to be? Is there something that we've been doing, and we've been doing a fair amount of it for root locus, that will help us figure out these angles? Do you remember where we've been using angles to this point? We did a lot of it at the beginning of last class, where we were trying to look at where we were on the real axis. Do you remember how we put a bunch of numbers in and we saw, does it equal 0 or 180 degrees? Was the only 2 cases we had. If it equaled 0 degrees, we knew that it wasn't a real plot, because we know that the angle of KGH evaluated at S to be valid, we know that that angle has to be plus or minus 180 degrees. So it's the same thing over here. If we can use this starting point and we can calculate what that angle is for that particular point, we can figure out what does that angle of departure or angle of arrival going to be. So we're going to go ahead and do that. So this is just kind of summarizing where we have our closed loop and sorry, back up our open loop transfer function with, we have, let me minimize this, is kind of in my way. I have 1, 2, 3. Well, let me put 3 zeros or 3 poles and 1 0. And so now we can start to populate a little bit about what this root locus does. We know that we have a pole that exists between the odd and even going from right to left. And so we know we start at a pole and we end at a 0. So we know that this root locus is taken into account. Now, the problem is that these two complex conjugate pairs, we're really stuck. We don't necessarily know which way to go. So what we want to do is we want to calculate that next angle, because we know that they're going to end up going out to some pole or some 0 at s equals infinity. Okay, so that's our step. Excuse me. So we're looking to calculate what our angles are of departure. And then we're also going to look at, because we have 2 finite zeros, remember n minus m equals 2. We have two root loci that approach infinite zeros. So what that infers, what that means is we would have to go ahead and calculate the angles of the asymptotes. But if you remember and you think about it a little bit, we know we actually have 2. We have one at plus 90 and one at minus 90, or 270 degrees. So we got the real axis one. Let me go ahead and erase that one. And now we're going to calculate our departure angles, and we're going to pick a point that is near one of the complex poles. And our points, again, must be equal to 180 degrees. So this point here, we know that our theta for P1 is going to be calculated based on that direction. What about the departure for P2? So let's keep going. Let me move this out of the way. So our characteristic equation, again, is 1 plus kgh. Our angle has to be plus or minus 180. And remember this, okay? We've got 4 poles. We have our 0 here. We have we have 3 poles and 1 0. And so if you recall, we're going to have an angle theta z1, and we're going to have a pole theta p1. Sorry about that. And we're going to have a theta p2, pole 2, and a theta for p3. Remember, these are all the angles that I have over here. And what I'm going to do is I'm going to take and find that this has to be equal to 180 degrees, plus or minus 180 degrees. So if I want to calculate any one of those angles, say if it's departing from here, theta p2, then that's going to be defined as my angle of departure. So this is my theta sub d. And now I'm going to go ahead and plug that in to this particular point, or this particular equation, which I have to calculate what theta z1 is. Then I'm going to subtract the sum of theta p1, theta sub d, and theta p3, and I'm going to set that equal to 180 degrees. So, so let's see. So now I know that this angle is 90. So this is theta p1, this is theta z. So I'm going to try to calculate all these angles to get to this point. So I've got my theta p1. So I'm basically trying to get to -1 plus j1. So -1 plus j1. So I'm calculating all those angles. So I've got to solve for my angle here. My angle here, which you can see is at 45 degrees. This one's unknown. And then this last one, there's some stuff in the way. Oh. And then this theta p3 is going to be from this location over here. Okay. So that's the approach that I'm going to go. And when I calculate it, my angle of departure is 108 minus or minus 256, right? Because I could go plus or minus 256. So let's go ahead and do this by hand. Let me bring up whiteboard here. Okay, so help me out. What is my open loop transfer function? I'll take a volunteer. Open loop transfer function. Anybody want to guess or tell me what it is? Remember, all we have to do is look at the poles and zeros, and we can tell that, right? So our poles, we have -3. And then we have -1 plus j and -1 minus j are our 3 poles. And our zeros, we only have the one at -2. So my open loop transfer function, if you're ever stuck doing this, just put in s minus your 0, so s minus 2 in the numerator. And then in the denominator, I have s minus a -3 times s minus a -1 plus j. Let me put parentheses around that. And then s minus a -1 minus j. And that'll give me my values, okay? So simplifying that down, s plus 2, s plus 3, s plus 1 minus j, and s plus 1 plus j. All right, so now we're trying to figure out what this angle of departure would be. So for a volunteer, let me calculate. So find what that angle of departure needs to be. So we're going to find it over here. And remember, well, let's just go ahead and set it up, and then we'll figure out what that needs to be in a moment here. All right. So we're going to go ahead and we're going to plug in our open loop transfer function. So we're going to plug in at s equals -1 plus j. And we're going to do that for all these points except this one. This is the angle we're going to try to calculate, okay? So this one here is just going to be left as a magnitude and an angle. So we're going to do -1 plus j plus 2 over -1 plus j plus 3. I'm skipping this one, right? So I'm going to just do magnitude and angle. This is going to be my angle of departure. And then sorry about that. And then I'm going to put in here s, not s, -1. Why is it doing that? So this is -1 plus j. Geez, my writing is all over the place. Sorry about that, folks. Plus j. And then I have to add +1 plus j. All right, so I've got to do magnitude and angle of my +1 plus j all over 2 plus j. This is unknown. And -1 and +1 cancel, so this is 2j. All right, give me some angles, please. Any angles? Well, this one should be pretty easy, right? The numerator is 45. What about over here? What is the angle of 2 over j? not hard. If you get stuck, we have 2, and we go up 1j, right? So what is the angle associated with that? What does Sakatoa say? The inverse tangent of 1/2, which is equal to, let's bring that up in MATLAB. So a tan of 0.5, multiply that by 180 over pi, 26.56 or 57. So that's the angle we have here. This is just theta d. I don't know what that is. I've got to solve for that. Because again, I'm not looking for the particular angle at that point. I'm just trying to figure out what angle it needs to be to get there. And then lastly, what is the angle of 2j equal to? What is the angle of 2j? This should be a really easy one.
0.
This is equal to 0. This is equal to 2, right? So all I have is this. What is the angle? How much do I need to rotate to get to that one?
It's just 90.
90 degrees. Okay. So now I know that this has to equal plus or minus 180 degrees to be valid. So it's 45 minus 26.57 minus theta d minus 90 is going to be equal to, let's just call it the plus 180 to start out with that. So continuing on, let's see, 45 plus 90 is 135 minus 26. Oops, this is plus and plus. Sorry about that. Do that again. So 45 minus 90 is minus 45 minus 26.57 plus theta d equals 180. Theta d is equal to 180 plus 45 plus 26.57. So let's see. So that's 206.57 and 206 plus 45. Is that equal to 251.57? Did I do that correctly? I think I did that correctly. Can somebody check my work? The other option, well, I don't know if I can do that as another option. But 251.57. Okay. Questions on that? Let's see how that compares to this. So let's see, 71.57, 45 minus 90. Let's see. Slightly different. I do get the 108, but for some reason, I'm in the opposite direction. So let me look and see. Let me try that again. So I've got 45 degrees. That is correct. And we said the 2 over j. That's correct, right? It's the inverse tangent of the tangent is equal to Sakatoa, right? So that's the opposite. The tangent of theta is equal to the opposite over the adjacent. So if I'm trying to solve for theta, I take the inverse tangent of the opposite over adjacent, and that equals theta. And the opposite in this case is the imaginary part over the real part. So the tangent inverse 1 of 1 over 2 is equal to theta. So let me just go and double check to make sure. So the inverse tangent of, it shouldn't make a difference, it's 1 over 2 times 180 over pi. 26.57 degrees. So that looks like that's correct. This is theta d. This is 90 degrees. That's equal to plus or minus 180. So 45 minus 26.57 minus 90 minus theta d is equal to 100, and let's just do a plus 180 degrees. So theta d is equal to, well, let's do minus and then we'll do plus so we can get the plus on the side. So this is 180 minus 40, plus 45. How about that? Plus 45 minus 26.57 and minus 90. Is that correct? Is that what I have? Make sure I be clear there. All right, so 180 plus 45 minus 26.57 minus 90 is 108.43 degrees, which checks out with this angle here. I'll have to double check why that's 256. The minus 256 must come from, if this is, so that one's equal to 108. So we did that. It's writing. So that's 108. So that looks good. We can also plug in a plus 90. So 45 minus 26.57 minus 90 minus theta d equals positive 180 degrees. So theta d is going to be equal to 45 minus 26.57 minus 90 minus 180. So 45 minus 26.57 minus 90 minus 180. So I have a typo in my notes. It should be 251.6. Sorry about that. Let me fix that real quick. Let's see. Why is this coming up? I'll just call that 252. So I had a typo there. I apologize for the error, but we get the correct results. So question on that, because it's either going to be 108 degrees or minus 252. I'm either going to rotate 108 degrees to get that point where it takes off, or minus 252. And that's how we would calculate the angle of departure. All right, I'll give you 3 minutes. Okay, I would like you to calculate this angle. So 3 minutes to go ahead and calculate that angle. Right, it is 224. I'll give you the 227 to do that, okay?
Sorry, which one?
Calculate the angle of departure for this one. This is the only other one that you can calculate, because the other ones, they don't have an angle. They just kind of go to each other. So there is no other angle of departure or arrival. So calculate the angle of departure for theta P1. And I'd love a volunteer to help me come up with the answer for this one. One more minute. Okay, who'd like to volunteer to give me the answer? Somebody like to be volunteered for me? Or by me? How about Sean? Sean, do you have an idea how you'd solve that?
No, I just got the zeros and the poles. I was trying to figure out the angles still on
Well, how did you start? Can you tell me how you started?
I just got the zeros and the poles, and then I started to
This right
find,
here, you mean?
yeah, and then I started to find the angles for the S+3 and then the S+J.
Okay, so that's my question, which is you found the angles. What was your starting point to find the angles for?
Oh, I guess I'm not sure what you're asking.
So you're trying to find the magnitudes and the angles of the vectors between the open loop poles and zeros to the point where you're trying to calculate the angle of departure. So what I'm doing is I've got this. Oops, this one. I'm trying to calculate all these angles so that I can calculate what that angle needs to be to make that rule. So I want to know magnitudes and angles of all those, these elements here, and what vector length and magnitude as well as rotation needs to be to get me to that point. So do you know what those are? Or do you know your starting point, I should say? What are you evaluating at?
1 plus J.
Close. You need to do the transfer function that S equals -1 minus J, right? This is the point you're trying to get to. So it's -1 minus J. So you do that by plugging in -1 minus J plus 2 over -1 minus J plus 3. This is this one I know now. Who I'm trying to find, I should say. So -1 minus J plus 1 minus J. And this one I'm trying to solve for that point. So this is M at an angle of theta D. So I continue on. This is going to be equal to, not sure what happened. This is going to be equal to 1 minus J. This one's going to be equal to 2 minus J. This one is going to be equal to minus J. And this is magnitude at theta, or -2J, I should say. So this one, what is the angle? What is the angle for the first one?
Would they all just be the same but negative?
Say that again.
Would they all be the same angles, just negative?
Let's see. Would they all be? I think,
No, I don't
yes,
think
they
so.
would be because it's complex conjugate. So that's right. So that would be correct. That would be a negative angle. So this would be, instead of positive 45, that would be negative 45. Oh. This would be equal to minus, geez, I'm crow, minus 26.57. This is going to be equal to, or I can just put the angle. This is going to be equal to minus 90. And this is going to be equal to theta d. So now I have minus 45 minus negative 26.57 minus 90 minus theta d is going to be equal to plus or minus 180. If we start off with plus, then we have theta d is equal to minus 45 plus 26.57 plus 90 minus 180 degrees. And that's what doing the plus one. The minus would just be, you basically would just change that to a minus and that would be it. So that's how you find your angles of arrival or departure. You simply sum the angles. Okay. So a departure angle is you're going to a pole, right? Or you're exiting from a pole. So at that point, you're trying to solve for theta d in the denominator. That's the departure. So this is if you're trying to find a pole, we know we have it over here. For a zero, a finite zero, we're actually going to be up here, correct? Because we're ending up for the angle that's in the numerator. So this is theta a. So if you'll notice, this is theta z minus theta p. That's what we expect. Over here, it's the opposite, right? It's theta p minus theta z because we've just swapped the directions around. And you can do that. You can see that over here, right? Because if you look over here, this is 45. This is the 0 minus the poles, right? The 0 minus the poles, either plus or minus 180 is going to be equal to your angle of departure, because when I move this to the other side, it becomes a plus. So you can see I have the plus over here. For the arrival angle, so I'll just put theta a over here, and I'll put theta 1, theta 2, and theta 3. Whoops. So this is going to be equal to theta a, which is I'm trying to solve for, minus theta 1 plus theta 2 plus theta 3 is going to be equal to the plus or minus 180. So now I have to bring these onto the other side. So theta a is going to be equal to plus or minus 180 plus, these are all poles, right? So these are all the poles, the angles of the poles. That's why it's plus. And if we had any zeros up here, it would be minus. That's why this equation is substituted that way. All right. So for the departure angles, you're going to a zero, a pole, you're leaving a pole, use this equation. For arrival angles, you're going to a zero, use that equation. All right. One more thing that we can refine. So if we are either crossing the j omega axis because we are approaching zeros at s equals infinity, or if our angle of arrival or angle of departure points are such that we have to cross the j omega axis, we can use our Routh-Hurwitz criteria and find our auxiliary equation. Because remember, we did the auxiliary equation, which was always some as squared plus b. And if we set that equal to 0, we always ended up with complex conjugate pair terms there. So if we have a root locus that, let's say we have 2 points, and we know that it approaches here and here, we know we can refine that and find out where it crosses the j omega axis by using the auxiliary equation. Okay, so we'll see that here in a minute. All right, so here's pretty much the sum of all the highlights for how to do root locus. So we know we're going to be symmetrical about the real axis, which means you have to have complex conjugate poles. Number two is the most important one, I think, in terms of understanding these things, is your root locus always starts at the poles and ends at the zeros of the open loop transfer function. And that includes any infinite zeros, okay? So make sure you understand that includes your infinite zeros. If you do have any infinite zeros, you can solve for those angles, those asymptotic angles, by taking your 180 and dividing by n minus m, the order of the denominator minus the order of the numerator. And then the centroid, where those asymptotes start, you sum the poles and you subtract the sum of the zeros, finite only, and then you divide by n minus m. Okay, that'll give you a way to adjust that. And then this is another one that really helps for all the root locus points that are on the real axis. You always go between odd and even poles or zeros. And you start from right and you go to left. So start at the right, label your poles and zeros. Just do it sequentially, 1, 2, 3, 4, whatever. And then your root locus lives on the real axis between the odd and even, and not between the even and odd, going from right to left. If you are on the real axis and you have to break away or get back in to the real axis because for one reason or another, you don't either end your root loci that are there, or you don't start your root loci there, you can go ahead and take the derivative of this equation and you set that equal to 0, solve for the roots, and that'll give you a bunch of points. And one or more of those points will be valid breakaway or break-in points for your values. The departure angle is, or the arrival angle, you use those equations, and we could add a seventh one if it's applicable. And I didn't include it on here because it doesn't always have applicability, but 7, and we'll put maybe, is use Ruth Hurwitz to find J omega axis crossing. And this is if applicable. That's why it's a maybe. Okay. All right. Let's look at a little bit of design. So we're going to develop a root locus for a system with a value of k. Remember, that's a proportional controller. And we want to go ahead and determine the range of k greater than 0 so that our percent overshoot is going to be less than 20%. So here is our, get this out of the way. Here is our open loop transfer function. So we're going to solve for the open loop poles and zeros. So we have here, and everybody see how I got these, right? All I have to do is figure out what do I plug in for S to get this at a 0. I can see that I plug in 2 and 4J. So positive 2 plus or minus 4J gives me these two zeros. Over here, I plug in S equals -2 and S equals -4. So my finite poles and zeros. So my P's and my Z's. Let's see, I have my poles -2, -4, and my 0 is positive 2 plus or minus J4, right? Now, I don't have any infinite poles because the order here, the highest order S term in the numerator, our SM term, would be S squared. In the denominator, our SN is also going to be S squared. So since these two are the same, that means that we have no infinite zeros. So our root loci will start at poles and end at zeros. So we don't have any theta A's or sigma A's. We are done. There's none to calculate. Because there are no values there. Now let's go ahead and put our real access segments. So we're gonna order, we're gonna label from 1, 2, 3, all the way up until we're out of finite poles and zeros. We're gonna order them on the real axis from right to left. This is 1, and this is 2. And it only exists between odd and even, right to left. So that's where it lives on the real axis. And we know we start at a pole and end at a 0, which means that we're gonna start, or we're gonna see that we have to leave the real axis because we haven't terminated the root loci. As a matter of fact, we're gonna have to end up someplace over here. So we have our directions there. So we need to calculate our breakaway points, right? The breakaway point, because we know we are leaving someplace, we just don't know what that is. So our breakaway point is you take the partial derivative of -1 over GH and set that equal to 0. Whoops, I'm not sure what's going on with the order. Sorry about that. So here's our KGH. I guess the animations, I got to fix those. So here is my -1 over GH. So essentially, all I have to do invert these and put in a 1, and I multiply these out. So this is, when I FOIL this is S squared plus 6S plus 8. Take the negative of that, and I get that over here. Over here, I've got S squared minus 4S plus 4, and then I add 16. So I have S squared minus 4S plus 20. Now, taking the derivative of this, I know we're not experts at calculus, so I'll show you this step. This is when you got to use the quotient rule, right? Or is it the chain rule? I always get those two mixed up. So if it has a numerator and denominator, so we have the numerator and the denominator, and I think it's the chain rule. Take the derivative of the numerator, multiply by the denominator, minus the derivative of the denominator, multiply by the numerator, all over d squared. So I'm going to put that up over here. So the first thing I need to do is take the derivative of the numerator. So I have minus 2s squared plus 6, or minus 6, sorry. That whole thing multiplies the denominator, s squared minus 4s. Whoop, I'm not sure what happened there. So s squared minus 4s plus 20. Now I've got to go ahead and take the derivative of the denominator. So the derivative of the denominator is, I've got to subtract that. So 2s squared minus 4 times the numerator. So this is minus s squared plus 6s plus 8, all over the denominator squared, which is s squared minus 4s plus 20. That whole term is squared. And I'm going to set that equal to 0. Well, the nice thing is when I set that equal to 0, that side divides out completely. So now I have a little bit of a mess to go ahead and simplify this down to solve for that and then do the roots. So I'm not going to ask you to do that right now. I'm going to end up with this. So if I take the roots of this equation, then I will know what those points are. All right, so I've got two roots. This is what I have over here. It's minus 2.88 or positive 5.28. So the question is, of those two roots, which one of those is a valid point that the root locus actually has the ability to get to? So remember, it has to be a point where the root locus actually gets to. Where on the real axis do you see the root locus living? And do those points, as 5.28, is there a root locus over there on the real axis? That's way out over here. So that's not a point. There's no root locus over there. Minus 2.88 is someplace over here. So this is our breakaway point, and it's the breakaway point because the root locus has to leave the real axis at that location. So that's our breakaway point. Now, how would you solve for K? Anybody know how you'd solve for K? Remember, my value of K is equal to 1 over GH negative. That's the magnitude evaluated at S equals R minus 2.88. So you can solve for K using this formula. Just solving for the gain that needs to be there. Okay. Anybody want to see that done, or do you feel pretty comfortable doing that?
Yeah, it'd be nice if you can go over it.
Sure. This one is a little bit easier because it's just the gain. So I'm going to plug in, and it's going to be close. So let's say S, we know that the 0 is minus 2.88. All right. So that's the value. So my GH is going to be equal to S minus 2, that quantity squared, plus 16. That whole thing, I put 15, sorry about that. That whole thing has to be divided by, let's see, we said S squared plus 6S plus 8. So all I did right here is I just took this is the GH, and I just rewrote it over here. Okay. Plug that in, that's that value of GH. My value of K is going to be equal.
I don't want to interrupt you, but you just put not like multiply
I'll
the
multiply
plus
by 8. Yes,
8.
thank you. Sorry about that. Plus 8. Is that what you meant, Joanna? So there's my value of GH. So now my value of K is going to be equal to the magnitude of minus 1 divided by GH. So that value of K is pretty small number, 0.0248. Okay. That's how you'd solve for that. All right, I got to clean some stuff up here because let me bring that back up because where did it go? The slide was getting too busy with my markup, so I apologize for that. So I have my breakaway points. I know where it is. It's a valid point. Now I've got to figure out the angles of arrival. Why are they arriving? Because I'm going. Oh, why isn't this writing over here? I'm going to these finite zeros. So I'm going to pick this one to solve for first, right? This one over here. So what I need to do is I need to figure out the length. Well, actually, I have it over here. Figure out the magnitude and angle over here, magnitude and angle over here, magnitude and angle over here. And the angle of arrival is going to be the sum of these, make sure you vectorially sum these, and then set that equal to plus or minus 180 degrees. So for this one, I'm arriving at 168.7 degrees, which means I'm coming in hot. I'm coming in at this crazy high angle. I'm going to do the same thing for this one, but I know it's complex conjugate pairs. So this is the other thing too. Once you know approximately this angle, you basically just mirror it on this other side and you get that angle. Now, the only other thing I'm going to do is figure out where it's going to cross the j omega axis. So I'm going to do my Routh-Hurwitz approach. So here's my Routh-Hurwitz table. So remember that the Routh-Hurwitz has to be done for the characteristic equation. So that has to be done for 1 plus k gh. I don't care about the numerator. I just care about the numerator of the denominator. So that's going to be s squared plus 6s plus 8. And then that's plus k times s squared minus 4s plus, I think we said 20. So that's what we have to do. That's the characteristic equation that we need. So when you set that up, we're only interested in this again. So what we see is we see, let's see, we have k plus 1 times s squared. That takes care of those. Then I have a 6s and a minus 4. So plus k times whoops, sorry about that. Let me do it the other way. Let's do the s term. And this we have a 6 minus 4k. And then lastly, we have, let's see, 8 plus 20k. And that's what we're going to put into our Routh-Hurwitz table. So our k plus 1 goes into our s squared. We skip, and then we put this into our s to the 0. And then our next one is over here. Now, we really don't need to do the Routh-Hurwitz. All we need to do is when we get a row of zeros, then we find the auxiliary equation. To make this a row of zeros, 6 minus 4k has to be equal to 0, correct? So k has to equal 1.5. Once we know what k is, now we're going to plug it into here. So k plus 1 times s squared plus 20k plus 8, evaluated at k equals 1.5. We're going to set that equal to 0, and that's going to be our 0 crossing points. So we have 2.5 s squared plus, let's see, that's 30. 38 has to equal 0. So if we solve for the roots of that, let me bring up MATLAB and type in roots of 2.5, 0, because there's no 0, because there's no s term. It's a 2.5, not comma, 0, and then 38. Am I fat fingering everything this lecture? And there are my roots. And that is approximately where it crosses, here and here, about 3.9 or so. And that's showing how you calculate that there. So now we pretty much have enough information to go ahead and finish drawing the root locus. So we just have to kind of approximate what the shape of that looks like. And that's where we just have to guess. We can't really, other than actually plugging in some different points for k, we really just have to kind of guess at its shape. Okay. All right, so now the last thing we need to do is we want our percent overshoot to be less than 20%. So this is when it's particularly important, where we're going to use these lines, because remember, this line right here is the cosine, or the inverse cosine of zeta. So that tells me that angle. So if I want my overshoot to be less than that, what I need to do is find a point and be on this side of that point. So I can pull this point off over here, and it looks like, it's kind of hard to see, but I don't know, 3, oops, sorry. So I'm eyeballing this approximately. So what is that? Minus, is a tough one. So let's say that's minus 1.75. plus J, I don't know, 2.9 or something like that, would be a point where our value of K. So we would pick our value of K based on that. And you can see you use MATLAB to do the root locus plot. And here is the pole. I said minus 1.75. Again, I was eyeballing it, plus J.29. MATLAB has it set this way. And then you can calculate the gain. So here's our pole. So now you go back to your transfer function. So K is equal to minus 1 over GH. You evaluate that at S equals minus 1.54 plus J 3.02. And you should get 0.41. The nice thing about MATLAB is it tells you what that value is, but you can check it over there. Okay. So K has to be greater than it has to be less than 0.41, because as we increase K, we go out in this direction. So our value of K has to be less than or equal to 0.41. And that's how you do the root locus plots. So this is just if you don't have it in standard form. If you have the closed loop transfer function, you kind of buried the GH. Here's our characteristic equation. We can set it up over here. This is just kind of teasing out how you can get the open loop transfer function. So it's just kind of backing it out from here to get this standard form. But that's, that's just an extra work to go ahead and do that. And that's pretty much it for root locus. Design, analysis, all that stuff. I don't really care about the last two. If it's not in standard form, we're going to assume for your testing purposes, you would have that to do that. Okay. Questions on root locus?
Hey, Paul.
Yes.
Can you actually go over some homework problems? Whatever the most recent one that we're tasked with.
I'm not sure I understand what you mean.
Can you
mean the
go over
root
some
locus
homework
stuff?
problems? Yeah, the root locus homework problems, I guess.
Well, I'm not exactly sure how much you want. I can get you started. You're still working on it, so
Yeah, like I get that like the third problem on the homework is totally about the class that we just took, but the homework number problem 2, I wasn't sure how to start with this problem.
problem number 2.
Yes.
So find the breakaway points. So those points, you're going to take the partial. Oops, that's the at sign. Hold on, let me just do it this way. So you're going to take the part.
Yeah, I'm sorry. I got the centroid of the asymptotes, but I think the only part that I was stuck in was just finding the partial derivative part.
Take the partial derivative of this one.
Yeah.
So you're going to take the partial derivative of minus. Let me just bring up the right equation. So that is number 6. So you can take the partial derivative of -1 over GH with respect to S. So take the partial of minus S times S cubed plus 7S squared plus 10S all over K. Oops, now I got to get the K out of there, sorry. All over this S squared plus 4S plus 8. Do you know how to do that?
That's exactly where I was stuck at. Sorry.
You don't know how to do the partial derivative for this one?
Wasn't quite sure because I did take a differential equation course, but it was just been a while So
Well, I'll get you started. So what you're gonna do, I recommend you multiply everything out, s to the fourth plus 7s cubed plus 10s is the numerator. And the denominator is s squared plus 4s plus 8. You're taking the derivative of that with respect to s. It's only the only variable. So now remember, it's the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared. So I'll give you the first one. If I can move up. Doesn't want to move up. Sorry, folks. So we'll do the derivative of the numerator, which is minus, these are all minus signs, sorry. So you have minus 4s cubed minus 21s squared minus 10. That's the derivative of the numerator times the denominator, s squared plus 4s plus 8. I'll do the whole thing for you because all I really need is this. You'll have to do the multiplication out, but I'll do the whole thing. Now I take the derivative of the denominator. So minus 2s plus 4 times minus s to the fourth minus 7s cubed minus 10s and set that equal to 0 and solve for those points. Make sense?
yeah, so we only care about that. Like we don't really have to have the square of the denominator at the bottom.
No, because when I set that equal to 0, when I multiply both sides by d squared, what's 0 times d squared?
Oh, okay. It's gonna be still 0 anyway.
Yeah. So you really only need to do this part here and get the roots for that.
Okay. Yeah, makes sense.
Good.
Thank you.
Okay. Anybody else have any questions? All right, well, next Tuesday, I'm the class with a review ready to go. Because on Wednesday during lab, we have test number 3. And as we talked about, you already have all the information in terms of the review. So you should have everything you need. Okay, anything else? All right, well, nothing else. Have a great weekend, everyone, and see you on Tuesday. Take care.